Okay, so today we are looking at a problem from Calc 2. Um, so there's a lot of techniques of integration in this part of calculus. So we're looking at this problem, and at first you see there's an x squared in the bottom and x squared in the denominator, and then in the numerator, and so you can't, probably not going to be able to use u substitution. That's always my first thought when I see something like this. But it doesn't really look like it has, a function within a function that's like a derivative of itself is hanging out in there somewhere, because they have the same power. If it was like an x in the numerator and an x squared in the denominator, then we could work with that, but probably not going to be able to use u substitution. So kind of moving through, u substitution's probably out. Integration by parts, it doesn't look like it's going to work either, just simply because we do have the same degree in the numerator and denominator. And it's going to be pretty messy, even if we were to split it out into two functions to be able to do integration by parts. Same thing with like long division. It's just going to be, it's just not going to be a clean thing for us. But if you kind of look at this, anytime you have something squared minus something squared or plus something squared, or you can change it into that, and then you have a square root, and this isn't, it's not written in square root form, but we do have something to the 5/2 power. So keep in mind that anything raised to the 1/2 or to the 3/2 or whatever can be written in radical form. That it's probably going to be a trig substitution problem. So that's going to be kind of our first thing, is we're just going to rewrite this as x squared over the square root of x squared minus 1. And then we're going to raise all of that to the 5th, just to kind of separate out the degree there, the power there, the exponent. Okay, so we have this, and looking at this bottom part, this is a big clue. Whenever you see this, like a square root of something squared minus something else, or plus something else squared, that you're probably going to need to use trig substitution. So we're going to come over here and draw our triangle. So we have a triangle like this. The reason that we do this is because this really looks like something from Pythagorean theorem, right? That if we were solving for one of the legs of the triangle, we would do a squared plus b squared equals c squared. And then one of the legs of the triangle would be the square root of like the hypotenuse minus the leg. So the hypotenuse squared minus the leg squared. So that's the reason we use a triangle to do a substitution, is because it looks like it came from the Pythagorean theorem. So it's going to be an easy setup for us, an easy substitution to make if we do it that way. So we have a right triangle over here. Whenever you have a minus sign here, you should assign this expression to be one of the legs. If this were a plus sign, if it was x squared plus 1, then assign that to be the hypotenuse. But since we have a minus sign, we're going to assign that expression to be one of the legs. And it actually doesn't matter which one. There's a lot of flexibility here, and it just works out no matter which way, whatever you use for your reference angle, whichever leg you decide to use, it kind of just all comes out in the wash. So it actually doesn't matter too much. Okay, so I'm going to assign it to the bottom leg. So we have that expression there. And if you remember from the Pythagorean theorem, if this was ABC, then we would have a squared plus b squared equals c squared. So that means if we were to solve for this side a, we would get a equals the square root of c squared minus b squared. So that looks exactly like this guy right here. So whatever our first value is going to be the hypotenuse, and then the b is going to be that other leg. So because c is the hypotenuse and b is the leg. So that tells us that this side over here, that c needs to be assigned as x. Yeah, those are kind of synonymous with each other in that equation down there. And it tells us that b over here needs to be signed as 1, because that matches up with that. Yeah. So, and that's going to follow that same pattern whenever you have a minus sign, that this first number will be the hypotenuse, because it needs to be the largest value, right? Otherwise you'd have a negative inside your square root. And then that second term is going to be your other leg. Because keep in mind, this is 1 squared, right? 1 is the same as 1 squared. Okay, so I'm going to erase this so that we've got a little bit of room. So what we're looking at now is we want to replace everything over in this integrand, and I forgot to add my dx here, with something in terms of a new variable theta. So I'm going to assign theta down here, but again, it actually doesn't matter. If you were to assign theta up here, your terms would be a little bit different, like you would use, cotangent instead of tangent or whatever. But it's all going to come out in the wash. Like if you do your reference angle from up here instead of from this angle instead of that angle, it doesn't make a difference. So don't stress too much about that. Oops, I'm erasing all kinds of stuff. So we've got this angle theta, and we know we want to replace x, so we'll write an expression for x. We know we want to replace this square root of x squared minus 1, so we'll write an expression for that, and then we'll also write an expression for dx. So let's start with x. So we want to get an equation for x in terms of theta. It would be really convenient if we can involve this side 1, because then we don't have to deal with this expression down here that's a little bit messier algebraically. So we want to involve this side and this side, and ideally we would want this x in the numerator, just so that we can not have to deal with solving it. It'll just already be in the numerator. It's easier to solve that way. So we have to pick of the 6 trig ratios which one to use. So we have the opposite and the hypotenuse, which is usually sine. We say sine is equal to the opposite over hypotenuse. But this time, since we want x in the numerator, we actually want hypotenuse over opposite. So we are going to use 1 over sine, which is cosecant. So I'm going to write cosecant of theta is equal to the hypotenuse over the opposite side, so x over 1. And we can multiply both sides by 1 to get rid of that one in the denominator. So we get cosecant of theta is equal to x. And then, so we have x. We also need an expression for the square root thing. So this time we want to involve this side down here. We want to involve him, that other leg, and again, it's ideally we would involve this 1 because he's really easy to work with algebraically rather than involving the other x. So with our reference point of theta, we want to involve the opposite side over here, and we want to involve the adjacent side. So adjacent and opposite is usually tangent, or yeah, opposite and adjacent. But this time we're going to use cotangent so that we can get that square root expression in the numerator. Oh my goodness. So we're going to do that, and I'm going to write that next to this over here. Okay, so we have that cotangent of theta. So instead of opposite over adjacent, it's going to be adjacent over opposite. So cotangent of theta is going to be equal to square root of x squared minus 1. And of course that's over 1, but I'm going to not include that for right now because it's the same as just the square root expression. Okay, so we have our square root expression taken care of. We have x taken care of. The last thing we need is dx. So to do that, I'm just going to take a derivative of each side. So dx is equal to the derivative of cosecant theta, which is going to be negative, oops, and I don't want to run into my other stuff over there. So let's maybe write it this way. Dx is equal to negative cosecant theta times cotangent theta, and then of course we have a d theta there. Okay, so at this point I'm ready to now do all of my substitutions. So we're going to come back over to this integral, and we have x squared, so x is equal to cosecant, so this becomes cosecant squared of theta. And then our expression on the bottom, the square root of x squared minus 1, is cotangent theta. So this becomes cotangent to the 5th because we still have that 5th exponent raised to the 5th on the outside. And then times dx, I'm just going to put it in the numerator rather than sticking it off to the side. So dx is equal to negative cosecant theta times cotangent theta. Let me stick that in parentheses so we don't forget about the negative sign. Okay, and there's a d theta there too. Sorry, I'll stick him on. Okay, so we have this, And it might look awful, but it actually looks a lot less awful than this thing did up here. Because now that we're in kind of the realm of trigonometry, we can use a lot of simplifications and identities and things to clean this up a little bit. So I'm just going to rewrite this. These cosecants can combine, and then we'll have that negative on the outside. So this is going to be negative cosecant cubed theta times cotangent theta all over cotangent theta to the fifth. And then we've got a cotangent theta on the top and 5 of them on the bottom, so we can actually cancel a little bit. We've got our d theta out here still. So this becomes negative cosecant cubed of theta over cotangent to the fourth of theta. And you might get to this point and think, okay, this looks a little better, but I still have no idea what to do. If you're ever at this point, it's a really good idea to just try and start changing things into terms of sine and cosine. And then you'll find that a lot of stuff is going to cancel out, or it will at least be clear what path to take. So before I do that, I'm actually going to separate things a little bit further. So changing this into negative cosecant theta over cotangent theta, and I'm just going to raise all of that to the third, and then we'll have one more cotangent theta down here on the bottom, because we've got 3 of them, and then one more will make that fourth power. And then, and then we've got a d theta out here. Okay, so what that allows us to do, I'm going to kind of make, well, we'll just do it right here. So cosecant over cotangent, we'll kind of work this out really quick. So cosecant is 1 over sine theta, and then cotangent is 1 over tangent, but tangent is sine over cosine. So cotangent is actually cosine over sine. And all of that's going to be equal. Obviously, if we have a fraction within a fraction, we can multiply by the reciprocal. So it's going to be 1 over sine times sine over cosine, just flipping that denominator. And those sine are going to cancel. So this becomes 1 over cosine, which is secant of theta. So yeah, so changing things in terms of sine and cosine can actually help us quite a bit. So coming back to this, we know that that expression, this entire thing right here, is actually just equal to negative secant cubed of theta, because we have that exponent still. And then 1 over cotangent, I'm just going to change that to tangent of theta. And again, if you look at this, you might see like, okay, well, secant and tangent, like they have a few, you know, one of them kind of looks like the derivative of the other. And we've still got this d theta here. So looking at that, we want to separate these out so that we have a function and its derivative hanging out together. So I'm going to rewrite this again as negative secant cubed, I'm just going to do 2 of them, and then I'm just going to bring the other one over here with the tangent. Tangent theta, d theta. Okay, so now that we have this, you can look at this and kind of say, oh, well, secant and secant tangent, those are derivative, like this is a derivative of that. So we can use u substitution here. So there's actually 2 substitutions in this thing, which is a little bit wild. So we're going to set u equal to secant theta. We're not worried about the squared right now because that will get taken care of once we do the substitution, and we can use the power rule to integrate. So du then is secant theta, tangent theta, d theta. And hey, look, that's right there. Beautiful. All that is du, and then this part is u. So we can change this integral to be negative u squared du.